Hello everyone. In this video, we're going to learn how to solve certain equations that may not look quadratic at first, but when we delve a little bit deeper into them, we'll find that they contain a quadratic form that we can manipulate and therefore solve the equations using quadratic methods we have learned in previous videos. What we mean by quadratic form is basically this form where you have some constant times the square of a variable expression plus another constant times the same variable expression plus a last constant equals 0. And the important relationship is that one of the terms has a variable expression that is the square of the variable expression in another term. Whenever we see this form, we know that we are in possession of a quadratic form, and therefore we can use the techniques we already have for quadratic solving. And we're going to learn this entirely through examples, so we're going to jump right into an example right now. Okay, a first look at this equation may not tell us that we actually have a quadratic equation like the ones we've been solving using the quadratic formula, etc. But this is what's considered to be an equation containing rational expressions. We've already seen equations like this, and now we're going to go ahead and try to solve it using those same methods to begin with by clearing the fractions. And we can see the LCD here will be x squared. And with this kind of expression where denominators contain variables, we always want to also think about restrictions, which include values of x that would make any of the denominators 0. Here we can see the only problematic value of x would be 0 itself. So we'll go ahead and state that as a restriction. So for our restricted values of x, we know that x should not equal to 0, and we know that the LCD for the entire equation is x squared. So we'll go ahead and multiply both sides of this equation by x squared, and of course we'll need to distribute here, and we'll do the same on the right side. So we'll end up with x squared times 1 minus x squared times 2 over x minus x squared times 80 over x squared equals 0 times x squared, which is of course just 0. Now if we cross cancel what we can here, we'll get x on the top here, and these two will cross cancel completely. So we'll end up with the equation x squared minus 2x minus 80 equals 0. Now this equation has now obviously turned into or been transformed into a quadratic equation, which we can now proceed to solve. With quadratic equations, of course, the first method we'll always try is to see if we can factor the one side out with the variables and the constant in it, and see if we can handle it that way, because that'll be the easiest way to go if it's possible. So when we look at this problem, it looks like we are able to factor it pretty quickly. We want two expressions here whose product is x squared, and for this location we want two numbers whose product is -80, and if you remember, the sum has to be -2. So we used to use this big X to get this kind of problem solved, factored, and this will work as long as the coefficient here is 1. You don't want to use this big X if the coefficient here is not 1. You'll just go with the trial and error, or by the methods that we discussed by grouping. So here we notice that we want the product to be -80, and we want two numbers whose sum is -2. And if you think about it for a little bit, you'll realize that negative 10 times positive 8 will do the trick, because as we know, the product of negative 10 and positive 8 is negative 80, and the sum is negative 2. So we'll go ahead and factor this in that way. X minus 10 times x plus 8, and we now apply the zero factor property. So we get x minus 10 equals 0, or x plus 8 equals 0. Solving the first one gives us x equals 10, and the second equation gives us x equals negative 8. Now, it's always a good idea to check, but remember, equations containing rational expressions like this are mandatory check problems. So even if you're not going to take the time to plug in and completely check these out, which I will leave as an exercise for you, we will do the minimum amount of check which is required with this, which is basically to do a restriction check. So we do a restriction check on 10 to make sure it's not one of the numbers that it's not supposed to be. And of course 10 is not 0, so it passes the restriction check. And we'll also do a restriction check on negative 8, which of course again is not 0, so it should be okay as well. So this one passes the restriction check as well. Now for the full check, definitely take the time to do so in order to make this video a reasonable length of time. I'll go ahead and leave the checks for you. So here we get the solution set containing negative 8 and 10, and that's how we solve it. So notice the equation was not initially quadratic in the sense that it wasn't exactly in the form of ax squared plus bx plus c equals 0, but it contained hidden in it a quadratic equation. So that's one of the problems we can attack using quadratic methods. So make sure you can handle that. We'll go to another problem now. So here's a similar problem. Again, it's one containing rational expressions. So we'll go ahead and deal with the restrictions first. We know that here u should not be 0, because 0 would make this denominator 0. U should also not be 5, because that would make this denominator 0. So we don't want u to be 0 or 5. We'll check for that at the end when we have the proposed solutions. And the LCD here is just going to be 3 times u minus 5, as you know. So 3u times u minus 5. So we'll go ahead and multiply both sides of this equation by 3u times u minus 5. So we get 3u times u minus 5, and don't forget we're going to distribute here, so it's going to get multiplied by basically all terms since we have to multiply on both sides. So times 70 over u minus 3u times u minus 5 times 70 over u minus 5. And on the other side, we have negative 1/3, which we're also going to multiply by the LCD, because we always have to multiply by both sides if we're going to multiply an equation by any number. So now we'll go ahead and cross cancel as much as possible. So here we notice that the u's can cancel out. In the next term, we notice that the u minus 5's cancel out. And on the other side, we notice that the 3's cancel out. So now we'll clean it up carefully, not leaving anything behind, to see what's left. So here we notice we have 3 times 70, which is 210. You do not want to distribute at this point, because that is opening up the door for errors. So we'll wait to do that later in the next step. So minus, we will take care of the 3 times 70 again, which will give us 210. And don't forget the u. and on the other side we have negative u times u minus 5. We'll make a quick check to see if we captured everything. We have 3 times 70, which is 210. We have that. We have the u minus 5, which is here, minus 3 times 70, which is negative 210. And then we have the u, which we have accounted for. On the other side, we have negative 1 times u, which is just negative u times u minus 5. This 5-second check can save you all the points on a test. So we'll go ahead and distribute the 210 now, and we'll get 210u minus 5 times 200 is 1,000, and 5 times 10 is 50, so we get 1,050 minus 210u equals, now we're going to distribute the negative u on the other side, so we get negative u squared plus 5u. We'll always watch the signs. So we have a little bit of a break here because these two terms will go ahead and cancel out. So we'll go ahead and do so. So now we basically have everything we need to move to one side. So we'll go ahead and move all the terms to one side. So we end up with u squared minus 5u minus 1,050 equals 0. So to do this by factoring, we're going to need to go ahead and take a look at the prime factorization of 1,050. We know that 2 goes into it 525 times. I notice 5 plus 2 is 7 plus 5 is 12, so this number is divisible by 3. We know it's not divisible by 2 anymore because it's an odd. So we'll go ahead and divide by 3. At this point, I will go ahead and get some help from a calculator, so which should not be problematic as long as your instructor is okay with that. I don't mind, and I don't personally mind calculators for these kinds of calculations. So we'll go ahead and divide 525 by 3, and we get 175, and 1 plus 7 is 8 plus 5 is 13, so that number is no longer divisible by 3, but we know it ends in 5, so it's divisible by 5. So when we divide that by 5, we get 35. We should be able to handle the rest now. So we divide by 5, we get 35. We know 5 goes into that again 7 times, and then 7 finally 1 time. So now we have the prime factorization of 1,050. That should help us factor this expression out. And of course, because the lead coefficient here is 1, we can go ahead and use the big X again. So we are looking for two numbers whose product is negative 1,050, but whose sum is negative 5, which tells us these numbers should probably be pretty close to each other. So we can see some possibilities here. For example, we notice 5 times 7 here is 35, and 2 times 3 times 5 will give us 30, which gives us two numbers that are pretty close to each other and within 5 of each other, in fact, which is what we wanted. So the trick now is to get the right signs. So since we want their sum to end up being negative, we know because the product is negative, they're going to be opposite signs, and since we want the negative to dominate, we're going to make the 35 negative, so negative 35, and we'll make the 30 positive. So now we notice that their product is negative 1050 and their sum is in fact negative 5. So we go ahead and factor this out using u minus 35 times u plus 30. We'll do a quick check. First times first is first, last times last is last. The inner product and the outer product give us the middle term. That's a quick check that will save you a lot of trouble later. So now we go ahead and apply the zero factor property again, and we get u minus 35 equals 0, u plus 30 equals 0, so we get u equals 35, or u equals negative 30. Now if you try factoring it for some time and you don't come up with the answer, of course you can always solve it by the method of completing the square or by the quadratic formula. Both of those are universal methods that will solve any quadratic equation with complex coefficients. So but this time it worked out. Remember that I'm going to leave the complete check for you, but we will definitely do the minimum amount of checking, which is the restriction check. We don't want either of the solutions to be 0 or 5, and of course both of them pass the restriction check. So this one passes, so does this one. So we can go ahead and safely write our solution set to contain negative 30 and 35. Again, an equation that at the outset did not look quadratic at all, but after we did some manipulation, we did end up with a quadratic form. In fact, directly so, because it is in our basic quadratic form. All right, so make sure that you can handle a problem like this, and we'll look at another example now. So here we have another equation of the rational expression variety. Again, we will deal with the restrictions first. Here, the restrictions mandate that x should not be 0 because it would make this denominator 0, or negative 1 because that would make this denominator 0. So we don't want x to be 0 or negative 1. And as far as the LCD, that's not too bad either. It's just going to be x times x plus 1. As always, I invite you to try these problems on your own before you rejoin the video. It's easy enough to pause. Okay, so we're going to go ahead and multiply the LCD on both sides to clear fractions. So we get x times x plus 1 times 8 over x plus 1 equals, of course, we're going to distribute on the right side. So each of these terms is going to get hit by the LCD. So we're going to get 3x times x plus 1 minus 5 over x times x plus 1. Now we'll go ahead and cross cancel as much as possible. Notice that we can cancel those there, and on this side we can cancel the x's. So now we'll carefully write down what's left without distributing at this point. So we have 8x equals 3x times x plus 1 minus 5 times x plus 1. Good habits in mathematics save you points and save you the hassle of having to redo problems. All right, so here we get 8x is equal to 3x squared plus 3x minus, now we're going to distribute the negative 5, so minus 5x minus 5, watching the signs. So it looks like we can do some simplifying here. Before we start moving things around, we'll always simplify each side completely. Another one of those good habits that will save you trouble later. So we get 3x squared minus 2x minus 5. Now both sides are completely simple, so we'll go ahead and move this to the other side to join the other terms, and we'll get left with 0 on this side. It's very important to write the 0, otherwise you have demoted your equation down to the level of an expression, and we never want to do that. So on this side we have 3x squared minus 2x minus 5 minus 8x. Subtracting 8x from both sides, we end up with 0 equals 3x squared minus 10x minus 5. Just through experience, this does not look factorable to me. You can give it a few seconds of trial if you like, but you're gonna realize this is not factorable. Now, there is a quick way to see if it's factorable or not. If you recall from our previous video where we introduced the discriminant. So notice here that a equals 3, b equals -10, and c equals -5 in our quadratic equation. So if we calculate the discriminant, which is b squared minus 4ac, we get -10, quantity -10 squared minus 4 times 3 times c, which is -5. So we end up with 100 minus, actually the minus and the other minus will multiply to give us plus. 4 times 3 is 12, times 5 is 60. So we get 160. Now it is greater than 0. We know we can expect real solutions, but it's not a perfect square. So we know that it's not factorable. So we were right on our hunch. And now we can go ahead and proceed with other methods. So let's go ahead and use the method of the quadratic formula. So we have a, b, and c already written out there, so we know that the quadratic formula, we will always write it as is without plugging in to be safe, and then we'll substitute. So we get -b plus or minus square root of b squared minus 4ac over 2a. So we know that the opposite of -10 is 10, so we get 10 plus or minus square root of, we already calculated b squared minus 4ac, so we'll go ahead and use that. So it was 160 over 2a, so that's 2 times 3, so we end up with 10 plus or minus, we'll go ahead and break this up to simplify it. So we have square root of, you know that we want the largest perfect square factor of 160 in here. That should be simple enough with 16. And we'll put the non-perfect square product that's left in here, and that'll be 10. And downstairs we have 6. So we end up with 10 plus or minus 4 radical 10 over 6. And we notice a common factor of 2 on the top, so we'll go ahead and factor it out. That will leave us 5 plus or minus 2 radical 10 over 6. Now we can see that we can safely cross cancel those to leave us 3. So we end up with 5 plus or minus 2 radical 10 over 3, which is of course 2 solutions, one from the plus case, one from the minus. We can see that they both pass the restriction check, so we can go ahead and just put restriction check passed. And now we can write our solution set, and we'll go ahead and separate them. So 5 minus 2 radical 10 over 3 being one of our solutions, and 5 plus 2 radical 10 over 3 being our second solution. Very important not to use parentheses here because these are two distinct solutions for the same variable x. So that's how we handle a problem like that, which is not factorable, and this should all be reviewed. Anyway, again, another equation that did not look quadratic at first, but as you can see, we ended up solving it using quadratic techniques. All right, so here we have another equation to solve, and we know how to handle these equations containing radicals. We need to go ahead and square both sides to get rid of that radical. And again, remember that equations containing square roots, because of things that may go wrong with square roots getting undesirable numbers underneath, such as negatives, etc. These are mandatory check problems. So remember that we're going to check these for sure. So we're going to go ahead and square both sides. So we get square root of 9x minus 18 squared equals x squared. We want to leave the original equation alone and just not get lazy and just write squares there, because we want to go back at the end and check the original equation. So always try to preserve your original equation as is without writing anything around it. So we get 9x minus 18, of course, because we know the square root of any number squared is just itself. And on the right side, we have x squared. You can see that, again, we have a quadratic on our hands. So we'll go ahead and move everything to the right side and leave ourselves 0 on the left side. And this looks pretty factorable to me. So let's go ahead and try it. So it looks like if we just use x minus 3 and x minus 6, we should be in good shape. We'll do a quick check. First times first is first, last times last is last, and the inner and outer products seem to add up to the middle term. So we should be fine there. So now we apply the zero factor property and get either x minus 3 equals 0 or x minus 6 equals 0, which ends up giving us x equals 3 and x equals 6. So we'll go ahead and check 3. We want to know if the square root of 9 times 3 minus 18 is equal to 3. We're just substituting 3 every place we see x in the original equation. So we want to know if the square root of 27 minus 18 is equal to 3. 27 minus 18 is 9, so we're trying to see if the square root of 9 equals 3. At this point, we know that 3 does equal 3, so 3 made the original equation true, so it is a solution. And we don't need the question mark anymore. We verified it. So now we'll go ahead and check 6. So we want to know if the square root of 9 times 6 minus 18 also equals 6. And the square root of 9 times 6 is 54 minus 18. We want to know if that equals 6. Of course, 54 minus 18 is 36, so we're trying to see if the square root of 36 equals 6, and of course, that is 6, so we get 6 equals 6, and we don't need the question mark anymore. This one also passed the test. So now we can confidently write our solution set to contain our two x values, 3 and 6. And that's how we do a problem like that. Here's another one containing square roots. Go ahead and try it on your own first before you come back. All right, so we'll go ahead and square both sides. Notice that the original equations do not look quadratic, neither this one nor the previous one. But once we square both sides, we end up with a quadratic equation with which we can use quadratic techniques. So here we get 9t squared equals 4 minus 16t. And let's go ahead and move everything to the left side. So we get 9t squared plus 16t minus 4 equals 0. This one, if you notice, has a perfect square in the square position, and also a perfect square here in the last position. So you may get tempted into thinking that this will be a perfect square trinomial, and the only problem is that there's a negative here, and perfect square trinomials never have a negative in the last position, so be careful with that. All right, but let's go ahead and see if we can go ahead and factor it anyway. So also remember, this is a mandatory check problem because of the square root. So let's see, we can try 3t and 3t and maybe 2 and 2. That'll give us 6t here and 60 on the outside. That's not going to get the job done. So we'll go ahead and try another combination. You should never give up on a pair like 3t and 3t until you've tried all the possibilities for the 4. So maybe if I put 1 here and 4 there, I end up with 3t here, 12t here. I still can't get 16t out of that. So now I'll give up on the 3 and 3 scenario, and we'll try another combination before we give up and go to the quadratic formula or completing the square. So let's try 9t and t, and maybe try 2 and 2. That looks more promising. The inner product is 2t, the outer product is 18t. I can get positive 16t out of that as long as the 18 is positive and the 2 is negative. So that means we want the negative here and the positive here. So let's quickly check. First times first is first. Last times last is last. Pay attention to the signs. The inner product is negative 2t. The outer product is positive 18t, which do combine to give me the middle term. So we've done the check. It works. So now we get 9t minus 2 equals 0, or t plus 2 equals 0. So on this first one, we get 9t equals 2, so t equals 2/9. On the other side, we get t equals negative 2. We're going to go ahead and check the 2/9. So we want to know if 3 times 2/9 is equal to, with the question mark, of course, the square root of 4 minus 16 times 2/9. And 3 times 2/9 we can simplify here. We end up with 2/3. So we're trying to see if 2/3 is equal to the square root of 4 minus 32/9. We need a denominator here of 1, so we want to know if 2/3 is equal to the square root of course, we're going to have to multiply this by 9, this 1, and do the same on the top. So we end up with 36 minus 32 here, which is 4, and downstairs we're going to have 9. And of course, the square root of 4/9 is 2/3. So we get 2/3 equals 2/3. This one checks out. Now we'll go ahead and check negative 2. And so we have 3 times negative 2. We want to know if that equals the square root of 4 minus 16 times negative 2. And we really don't need to go much further because this is a negative number, and the square root of a real number, no matter what it is never going to be a negative number. So literally we can stop here. But just to make it look a little bit nicer, let's go ahead and go one more step. -6, we want to know if it's equal to, this is positive 32, so the square root of 36. And of course, we know that -6 equals 6 is a contradiction. Therefore, this one did not work out. And so there's only one solution, namely the 2/9. So this is a good problem because it shows you the extreme importance of checking when it comes to these square root equations involving square roots. So now we're going to write our solution set, and we're going to be careful to only put the 2/9 in there. So make sure that you are careful with these and you check these. So try to do this on your own if you haven't done so already. Make sure you can handle it, and then come to the next screen. Okay, let's go ahead and try this one now. Again, as always, try it on your own first and then come back. So here we're going to go ahead and square both sides. So we get -x squared equals the square root of 14 minus 3x over 5 squared. So on this side, we're just going to get x squared because the negative is being squared also. And on that side, we get 14 minus 3x over 5. And of course, if we throw a 1 here, we see that we're in the form of one fraction equals another fraction, which means we have a algebraic proportion on our hand. The best way to handle a problem like that is to cross multiply. That says AD is equal to BC. This is called the principle of cross multiplication, and your best friend, as long as you only have one fraction, equals one fraction. So we're going to get 5x squared equals 14 minus 3x. So now we'll go ahead and move all terms to the left side. So we get 5x squared plus 3x minus 14 equals 0. Let's go ahead and try to factor this. Since 5 is prime, this shouldn't be too bad. So 5x and x. We want to get 3, so let's try 2 and 7. And we want the 3 to be positive, so we'll make the 7 positive and the 2 negative. Now let's check it. So first times first is first, last times last, pay attention to the signs, is last. The inner product is positive 7x, the outer product is negative 10x, which end up to be negative 3x, which means we didn't have the placement of these correctly. So now we're going to change it. Let's put the positive, the negative here and the positive here. So now we have the inner product is negative 7x and the outer product is positive 10x, which does give us positive 3x. So that's the good combo. And notice first times first is still first, last times last is still last, and the inner and the outer products do work out this time. So now we go ahead and set each one equal to 0 by the 0 factor property, and we get x plus 2 equals 0. So 5x equals 7, x equals 7/5, and here we get x equals negative 2. So now we're going to go ahead and check both. So we'll check x equals 7/5, and we want to know if negative 7/5 is equal to the square root of 14 minus 3 times 7/5 over 5. So this time we are actually going to realize that we can stop, because the square root of no real number is going to be a negative number. So this one did not work, but we'll try negative 2 now. So we want to know if the opposite of -2 is equal to the square root of 14 minus 3 times -2 over 5. This definitely looks more promising because at least we get a positive number on this side. We are still checking. So we get 14 plus 6, which is 20 over 5. So we want to know if 2 is the square root of 4, and of course the square root of 4 is 2. So we get 2 equals 2, and this one works out. So again, highlighting how important it is to check these solutions. And the solution that works is x equals -2. Be really careful not to put the end of your check. That's a common error for students. They put 2 as the solution, but the solution is actually x equals -2. And of course, in the solution set, you don't put the variable, you just put the numerical value of the variable that is the solution. And there we have that. So again, please make sure you can handle this with no help before you proceed. Okay, so here we have an equation that looks slightly different from the ones we've been looking at, but we do notice that this required quadratic form is in play here, because remember, as long as you have one term with a variable expression which is the square of another term's variable expression, you do have quadratic form. And notice, if you take x squared and square it, you indeed get x to the 4. And then we also have a constant. So we are in the quadratic form that we are interested in. And the way we like to handle these is by using a substitution. You could do it directly, and I'll show you that as well, and then you can take your pick. I recommend the substitution method. You're less likely to make an error. So the way we do the substitution is we usually use the letter U when we want to do substitutions in mathematics, but of course you can use any letter you like. So here we're going to go ahead and let U be x squared. Now notice that if U is x squared, then U squared becomes the square of x squared, which is of course x to the 4. So now where we see x to the 4, we're going to substitute u squared, and where we see x squared, we're going to substitute u. So now the original equation turns into a new equation in the variable u. So minus 29u plus 100 equals 0. Notice where we had u squared, x to the 4, we put u squared. Where we had x squared, we put u. So now we have a new, simpler, and clearly quadratic equation in u, no longer in x. So that's a point to remember, because we have to do something with that later. So now we go ahead and factor this. Notice that's pretty easy to factor, because you know 25 and 4 give us 100, and they also have ways of getting 29 in them. So we go ahead and go with this, and we know they both need to be negative. So minus 25 minus 4 should do the trick. Now we go ahead and apply the zero factor property, and we get u minus 25 must be 0, or u minus 4 must be 0. So we end up with u equals 25 and u equals 4. This is when we arrive at one of the common errors with a problem like this. Students just go ahead and plug in 25 and 4. And of course that is not correct, because we're not solving for u, are we? We're solving for x. So once u has served its purpose and it has gotten us to the point where we have solved for it, then we go ahead and go back and substitute what u actually is. And we know that u is equal to x squared. So now we go back and we substitute x squared instead of u. So we get x squared equals 25 or x squared equals 4. These, of course, we can quickly solve with the square root property. If you remember, it states that if x squared equals k, that implies x must be either positive or negative square root of k. So we get x equals positive or negative square root of 25, which is, of course, simply positive or negative 5. And here we have x squared equals 4, so we get x equals plus or minus square root of 4, so we get x equals plus or minus 2. So you should definitely plug each of these in. Notice we have actually 4 solutions here. So plug each one of them in to convince yourself that it works. And once you've done so, we can go ahead and write our solution set. So again, order does not matter in sets, but I do like to go ahead and put solutions in ascending order, because if we all agree to do that, then all our solution sets are going to look the same. Now you will find, especially in some older textbooks, you will find this as well. And they're both correct, you know, except, as I said, we used to let students write that, but a lot of students didn't realize that that's actually 4 solutions. So nowadays we like to actually ask students to go ahead and write them out to realize that there are actually 4 solutions here. All right, so there is one problem which was not obviously quadratic. This is not considered to be a classic quadratic equation, because a classic quadratic equation should be able to be put in the form ax squared plus bx plus c equals 0. You'll never be able to do that with this, but using a clever substitution, we did turn this into a new quadratic equation, but in a different variable. We solved it for that variable, and then once we did that, we went ahead and substituted back x squared for u, and we got the actual x solutions. All right, so make sure you can handle that, and then we're gonna move on to one more problem. All right, so we've arrived at the last problem we're going to do tonight, and go ahead and definitely try it on your own before you come back to the video. It'll be great practice for you. Okay, so we're going to go ahead and move everything to one side first before we do our substitution. This is very similar to the previous one, if you notice, but it will have a couple of twists and turns that are interesting. That's why I wanted you to see it. So we have 2x to the 4 minus 9x squared plus 5 equals 0. Now we go ahead and make our substitution. So we're going to let u be x squared, which means u squared is going to be x to the 4. So when we make our substitutions, we end up with 2u squared minus 9u plus 5 equals 0. So now this expression here is a tough nut to crack, because you're going to find out after trying for a bit it is not factorable. So that's not a problem, of course, because we have 2 methods which are universal and let us solve any quadratic equation. So convince yourself that it is not factorable, and then we're going to go ahead and proceed to solve it using the quadratic formula. You could, of course, use the method of completing the square, but because of the numbers involved, it's going to be a little bit easier to just use the quadratic formula. So usually if the lead coefficient is 1, the method of completing the square may even be quicker than the quadratic formula. But when the lead is not 1, you're usually better off using the quadratic formula. So we're going to get u equals, as always, we'll just state the quadratic formula without plugging anything in yet. Plus or minus square root of b squared minus 4ac over 2a. Let's list the values of a, b, and c. We know that a is 2, b is -9, and c is 5. So we get the opposite of b, which is -9, will be 9 plus or minus square root of b squared, which is going to be 81 minus 4 times a, which is 2, times c, which is 5, and then divided by 2a, so that's 2 times 2. So we end up with 9 plus or minus square root of 81 minus, that'll be 20 times 2 is 40 over 4, which is going to be 9 plus or minus the square root of 41 over 4. Once again, it's very tempting to just go ahead and type those in as your answers into whatever system you're using, but remember, those are values for you. Those are the solutions of the equation that we created through the substitution, which was quadratic and gave us these two solutions. Now we have to go back and get the solutions for x. So let's split those two solutions up. One of them is u equals 9 minus square root of 41 over 4, and the other one is u equals 9 plus square root of 41 over 4. So now we go ahead and replace u with x squared. So we get x squared equals 9 minus square root of 41 over 4, which incidentally does happen to be a positive number, because think about it, the square root of 41 is not going to be more than 9. It would have to be a number larger than 81 for that to happen, because we know the square root of 81 is 9. So, and this is obviously less than that. So we know this is going to be positive, and this is obviously positive. So we're not going to have complex solutions, but they will be very interesting looking solutions. All right, so, and on this side we get x squared equals 9 plus square root of 41 over 4. So now we're going to apply the square root property twice. We're going to get x equals, remember, if you have x squared equals k, that implies x equals plus or minus square root of k, whatever k happens to be. Well, k happens to be all of that, and in this case, all of this. So we're going to get x equals plus or minus square root of 9 minus square root of 41 over 4. And on this side, we're going to get x equals plus or minus square root of all of that. So 9 plus square root of 41 over 4. And of course, notice that the denominators are going to end up just being square root of 4 if we split it up. So it'll be beneficial to split it up, because remember, an expression is not considered simplified as long as you have a radical in the denominator. So if that did not happen to be a nice 4, we would actually go ahead and rationalize the denominator. So we get a plus or minus, let's not forget our plus or minus, square root of 9 minus square root of 41 over 2. And on this side, we get x equals plus or minus square root of 9 plus square root of 41. Actually, this should be smaller, over 2. So notice that that's actually 4 solutions. So we'll go ahead and write them out separately in our solution set. So we have negative square root of 9 minus square root of 41 over 2, and negative square root of 9 plus square root of 41 over 2. Now we'll go to the positive cases. So then we have the square root of 9 minus square root of 41 over 2, and we have the square root of positive square root of 9 plus square root of 41 over 2. And that is all of our solutions contained in one solution set. So of course the order does not matter. You could have put them in any order, but I stuck to my rule of going in ascending order. I guess I tried. I'm pretty sure it is in ascending order, but that's basically how you handle these. And here we have seen equations that contain hidden quadratic forms that, once discovered, can be solved using our familiar quadratic techniques. All right, so make sure you practice these and become comfortable with them, and be safe until our next video.